Hello, I'm Ezra Sukay. I'm a rising third-year graduate student at Johns Hopkins, and I'm going to be talking about the coffee pot, which is a galaxy at redshift 2. And here's my attempt to get you to understand why we named it that. So here are some RGB images. The left is from shades going from the near UV to the near IR. And I show the red and the blue on the right side. And we also have contours from ALMA, 1.3 millimeter. And flux in that is twice as much as could be explained by star formation. Those galaxies hosted in AGN. Here's the UV-VJ plot showing that this is a blue star-forming galaxy. We have the star formation rate stellar mass with the star-forming main sequence that this galaxy lies above. So it's very actively star-forming for its mass. And then we have the radius stellar mass plot, which shows that it's a pretty normal size. And then I hope you were at Susan and Celia's talk on Tuesday, because I'm not going to get into the nitty-gritty of this. This galaxy was observed with GARDEN, which is a Cycle 1 JWST program using MSA on NearSpec. We did 5 steps on this object, and we observed the center twice. And this gives you an idea of the parts of this galaxy we covered with all this stuff. So this is the integrated spectra. Still working on our reductions, it's a little noisy. But we've labeled some prominent emission lines, and the one I want you to focus on is helium-1. And so we'll zoom into that. The next to helium-1 is a sodium absorption doublet. And it's not really clear if you can see it or not with the noise levels in this. What is the sodium V absorption doublet? So when you have neutral sodium, it absorbs UV light. You can go into 2 higher states due to the fine splitting structure. And you can see this in late-type stars, like our own star, which is why it's the Fraunhofer D line. You can also see it in E less than 10^4 neutral gas in the ISM and also molecular clouds. And you can also use it to trace old neutral gas in outflows with Luca, Crystal Martin, and Chen, all done. And the way you distinguish between all of these can be, for the stars, you can use SED fitting or the magnesium-1 triplet traces ionization in the photosphere of stars and isn't in the ISM. You can use that to isolate it. And then the ISM and the outflows, you'll see the outflows being shifted to systemic velocity. So taking advantage of our spatial resolution, we can start to look at bins instead of just a whole integrated galaxy. And when you do that, you start to see the sodium V absorption more clearly. So in these 2 leftmost star-forming clumps, you start to see the projection of it. Getting even more granular, it starts to look a little bit more like how you would expect sodium V to look. And these are, in this lowermost star-forming clump, and also this slightly higher lower star-forming clump. And then I went through spaxel by spaxel and identified where we could see these sodium Vs. Don't want to subject you to all of those. But here are those plotted on an RGB. So like you're seeing in the bigger integrated ones, these 2 star-forming clumps have sodium V absorption, and we also see some in this central star-forming clump. And so they're all sort of surrounding this central, very dusty region. This makes sense. Nancy et al. Found that sodium deabsorption and stellar reddening are related up to a point. Once stellar reddening gets so high, everything is extincted, and then you don't see sodium deabsorption anymore. That kind of explains why we don't see it in the center. Here I've plotted the attenuation in the V-band from SEG fitting to the broadband photometry. And so you see the rest of our sodium D absorption in places with high A sub G, not the highest. One of the reasons we're really interested in the sodium D absorption is to try to measure if there is or is not an outflow in this galaxy. And one of the canonical requirements for an outflow is to have star formation rate surface density above 0.1 solar masses per year per kiloparsec. And so this is a star formation surface rate density plot from our SED fitting. So you see that sodium D absorption lies in those areas with high star formation rate, surface density, but not the highest either. And I've overplotted the ALMA contour on here as well. This work is really preliminary, but we're hoping to add to current literature. There's studies with various lines like Prosper Schreiber 2019 looking at H-alpha outflows in C2 galaxies. And there's been the recent Davies 2024 paper looking at sodium D absorption in D2 galaxies specifically. But those aren't spatially resolved, so we're really hopeful that this will lead to really cool results. Thank you for listening to my talk.
Okay, here we go. Sorry about that. So Mark showed at some point some images of like clumps, and then there was one that was turned out to be like a background galaxy or something. Have you looked for this? Is it possible that some of these clumps are not real clumps in the galaxy?
Yeah, we have looked at this. I don't have the best plot for this out. The one indication that's not happening is that we do see strong helium absorption in a lot of these fractals, and we see really strong H-alpha absorption, and we see those at velocities that are consistent with being associated with the galaxy. I don't think that's likely, but you can see two things at the same time, and I haven't looked for if there's like a second component to some of these. That would be an interesting thing to take a look at.
Okay, thank you. Any questions?
When you showed the spectra, I missed where the zero is. How high is is that a real number, 120, 150, or you don't know where?
Yes, this is the mega Jansky for radian. Sorry, I'll go back to the whole. It lets me. We do.
So I guess my point, and I wonder if you could comment, is that the percentage depression is small. Do I have that right?
The percentage
depression due to the absorption by sodium D.
Yeah, these are normalized, even though I don't have the scale on it. Like this is 0, this is half, and that's 2. So yeah, it's not super great percentage absorption.
Okay, good. Let's thank Ezra and all the speaker of the morning session.